Hi there and welcome to Chapter 10, Chemical Reactions. Let me add Chapter 10 to this. Well, whatever. Consider chemical reactions. Okay. Let me enlarge this. Chemical reactions. So just consider for a second that all the synthetic fibers and plastics used in clothing, housing, and cars are enhanced or helped made through chemical reactions. All the synthetic fibers and all synthetic flavors and additives in foods, the packaging for them and how they're preserved are controlled through chemical change. Synthetic drugs and vitamins that keep you healthy. Synthetic drugs and more drugs that keep you unhealthy and make you overdose. Fertilizers that make it possible to feed the billions of people on this planet. That can be nitrogen fertilizers, weed killers, insecticides, and mold and fungus inhibitors. All are enhanced and made possible by chemical reactions. So first off, we're going to go over chemical formulas. So this chapter is concerned with describing chemical changes and the different kinds of chemical reactions that occur. So first we're going to go over chemical formulas. So identify the elements. So we got two different types of formulas, and it's really simple, really straightforward. So the molecular formula that's listed here in the middle is the formula that shows the actual numbers of atoms in a molecule. So if I was to take the structure of a molecule and relate it into a formula, that's what I would use right there. And then to break it down even further, you divide to its lowest denominator. So like C4H9 is actually C8H18. It's just broken down into the smallest possible formula. Most of the time, almost all the time, we're going to use molecular formula because that describes the actual molecule. I don't know why we would ever use empirical formula. So, for instance, glucose down here, CH2O is its empirical formula. Well, its molecular formula is C6H12O6, and that's what we are mainly concerned about, is molecular formula. So, three more things to know. The formula weight is the sum of the atomic weights of all the atoms in a chemical formula. So, what is the molecular weight of table sugar? Well, first off, we're going to have to look up the molecular weights of each one. And of course, hydrogen is 1. Carbon is 12. And oxygen is 11. So what you end up doing, let's see. Get some text. No! Ugh. Sorry. So, carbon is 12 times 12 equals 144, plus H is 1 times 22. Sorry, I sometimes forget I'm being recorded. 11 if anyone's even watching this, I don't know. That's fine if you, and that's fine if you prefer just reading off the PowerPoints. That's perfectly fine. Absolutely fine. So there's the final 342 units. See how I got that? 12 carbons times 12 so and then let's see. There we go. 12 carbons times 12 atomic weight. 22 hydrogens times 1. And 11 oxygens times 16 for its weight. And you just add them up. And then, what is the molecular weight of ethyl alcohol? So carbon is 2 times 12 units. It's 24 units. H is 1 times, or H is 5 times 1 unit, which equals 5 units. O is, wait, there's actually 6 hydrogen in that molecule. So let's see, the actual weight is 46 units for the molecular weight of ethyl alcohol, also known as alcohol to the common college student. So, or moonshine, or bourbon, or active ingredient in most liquor drinks. So let's go over the percent composition of compounds. It's easy. Don't overthink this. So the percent composition, it's easy. You take the atomic weight of the element and divide by the total weight of the compound. Then just convert this into a percentage. So if you wanted to take the atomic weight of a peanut butter and jelly sandwich, in this example, imagine peanut butter as an element. You would take the weight of peanut butter and divide that by the total weight of the sandwich. Because you want to know how much the weight of the whole sandwich the peanut butter is. So, sodium fluoride. What is the percent weight of that? And you can see this on page 257. It goes over it all. Very good problem. Sodium weighs 23 units and fluoride weighs 19 units. So it's really straightforward because there's just 2 elements in it. And so the percent weight of sodium in the compound is 23 divided by 42 for the whole thing. And the percent weight for fluoride is 19 divided by 42. Really straightforward, really easy. Let's see the next slide. Okay, I wrote it out for you guys. So the first thing is to write the formula, as you see there, sodium fluoride. Then determine the formula weight, and then determine the percentage of sodium fluoride. So let's determine the percent composition of carbon in table sugar. Do I list it out? No. So I'm going to work it with you real quick. So carbon is 12 times 12 units, 144 units. Hydrogen is 22 times 1 unit, 22 units. Oxygen is 11 times 16 units, which equals, I don't even know this. Does the book have an answer? No. Well, let's see. 10 times 16 is 160, so 171. So then, to take the percent composition of carbon would be 144 units divided by the total for the whole thing. Not just everything else, but everything else and carbon. So that would be 315, 337. .1%. So I hope that example was good for you. Kind of really marching through this lecture tonight. Let's see, we're at 12 minutes. Huh. So, okay. Which I try to march through the lecture in a really general sense. I'm starting to dive more and more into details. Okay. It's resuming. Okay. Okay. So basically, we're going to have two parts to a chemical equation. We have reactants and we have products. Reactants are on the left side. They're what go into the equation. Products are what comes out. So we have, for instance, to make carbon and dioxide, you can have carbon and oxygen on the left side. Your end result is carbon dioxide. That's just one example. In this reaction, the carbon and the oxygen are reactants, and the carbon dioxide is the product. Just like above, carbon plus oxygen yield carbon. And this reaction is carbon monoxide. Let's see now. I'm trying to figure this, how best to say this. Okay, so in this example, I want you to be able to balance this above equation. So there's one simple rule though when you balance equations. Do not change the subscript numbers. So this gives us an example. Oxygen is 2 on the left side and 1 on the right. So we're going to throw a coefficient out in front, a 2. Because this will balance the oxygens in. But now we got another problem. We got 2 carbons, just 1 on the left. So you put 2 right there. And that balances out the whole equation. And now, of course, I can make problems that get really, really, really complicated. And I'm not going to do that. I could do it, and I know you would understand it. But I don't think we have enough time in this class. It might take 2 or 3 weeks worth of work. Okay. Let's see. Now we're going to get into the types of chemical. Oh, I like this slide. Types of chemical reactions. I like nice bright colors. Okay, we're on slide 15 already. Marching right along. So oxidation reduction reactions. Defined as a reaction in which electrons are transferred from one atom to another. So, an oxidation reduction reaction is when electrons are transferred from one atom to another. So the oxidizing agent takes the electrons, and the reducing agent gives up the electrons. This is one way to classify reactions. I want you to be able to identify the reducing agent and the oxidizing agent. I mean, it's right here on the slide, so you should know that anyways. I want you to just know this fact, not to be able to have to identify it, because another way to classify chemical reactions is the 4 basic chemical reactions. You have combination, decomposition, replacement, and ion exchange. Let me give you some examples, but first off, let's look at these. Combination. What do you think is going to happen? We're going to combine 2 things. Decomposition. You're going to break it down. So basically, this is the opposite of combination. Replacement. It's going to be just like if you replace someone in a football game. Then ion exchange. That's when you have two sets of ionically bonded compounds. You should know what ionically compounded means, which just means a positive and a negative together, and they just switch. Let me give you some examples. Combination. X plus Y yields XY. Mg plus O2 yields MgO. Decomposition, just the opposite. Replacement, X plus Y, or XY plus Z yields XZ plus Y. Then ion exchange is going to be like AX plus BY yields AY plus BX. I want you to be able to identify these and finish them out. So here's some examples. Al plus CuCl2. Oh wait, here's some more replacement examples. So the aluminum comes in and replaces the copper in that top one. Pretty simple. Sodium will come in and replace one of the hydrogen. You get NaOH. Zinc comes in and replaces the hydrogen. Ion exchange. Ions of one compound interact with ions of another. HCl, the hydrogen leaves the chlorine, combines with the other, and the sodium leaves that. And now, I mean, you can look at this and be like, man, what is going on? Or you can draw some arrows. Usually drawing arrows will help. Just draw an arrow of the chlorine and where the thing with the chlorine came from. And you're also going to know that, well, does this look like a combination reaction? No. Does it look like a decomp? No. Does it look like replacement? It could be close. Just kind of follow the ions. Here we're going to list whether each is a combination, decomposition, replacement, or ion exchange. So let's look at that top. Silver plus sulfur yields silver sulfide. Now let me look up these answers and make sure I'm giving you the right answers. It's a combination reaction. Next one, let's see. Aluminum. I'm going to say aluminum comes in here and replaces the iron. So I'm going to say replacement. Replacement reaction, yes. The next one, well, we got 2 on the left and 2 on the right. Usually that means ion exchange. Ion exchange, yep. The next one, 1 reactant on the left and 2 products on the right. Decomposition. Yep. Okay. So now we're going to get into another term that you need to know. And this is called Avogadro's number. You know what? This would be neat to explain who this Avogadro person was. Well, this guy named Avogadro, he determined that the number of atoms in 1 mole of a substance is 6.02 times 10 to the 23rd. So 1 mole of carbon contains 6.02 times 10 to the 23rd atoms of carbon. So now, go back and forth there. 1 mole means there's 6.02 times 10 to the 23rd atoms. So there's 6.02 times 10 to the 23rd atoms in 1 mole of a substance. So 1 mole of carbon contains 6.02 times 10 to the 23rd atoms of carbon. So how many atoms? So, and this also applies to every substance. So 1 mole of anything, 1 mole of eggs contains 6.02 times 10 to the 23rd eggs. Let's see. Thus, a mole of carbon with a mass of 12 will weigh 12 grams. Just really remember that. A mole of any element will be its atomic weight in grams. So list the mass in grams of these elements. 1 mole of oxygen would be 16 grams. 1 mole of nitrogen. Well, where's the... We have a periodic table. 1 mole of nitrogen would be 14 grams. And 1 mole of neon would be 20 grams. So here's some practice problems that I made for you guys. And you know what? Practice problems are really, really easy to put on a test. So the sum of all atoms in a molecule is its what? Its molecular weight. Sorry. Next one. What is the meaning of subscripts in a chemical formula? Number of molecules? No, because the molecule is the whole thing. So like H2O, H2O is the molecule. The 2 is a subscript with the H. Percent composition of that element? No. It's the number of atoms of an element in that molecule. Atoms are neither created or destroyed in a chemical reaction. That's the law of conservation of mass. I've gone over that several times. Now notice, chemical reaction. If I went to nuclear reaction, you can create or destroy atoms. It's totally different, and we don't really go over nuclear in this class. So, in a redox reaction, reduction is defined as what? The reducing agent, or the reduction is defined as gain of electrons. Oxidation is defined as loss of electrons. Here we go, calcium carbonate. What is this? It's decomposition. Pretty straightforward. What's this? Combination. Substances that take electrons from other substances are called what? Let me make sure I get this right. Yep. The oxidizing agent. So the oxidizing agent is what takes electrons from other substances. Something I haven't gone over yet, but you'll remember in lab that sometimes when we mix two substances, you got something at the very bottom. That is called a precipitate. It precipitates. Any substance that contains Avogadro's number of particles is called a what? Mole. It's a mole. Please complete Group A numbers 4 and 5 for me, please. I believe that's let's pause for a second.